Okay, last time we were discussing the asymptotic analysis, or what we can say that we were discussing the time complexity, although asymptotic analysis is the proper term, or the complexity analysis of an algorithm. And the last thing which we discussed was that we need to have the tighter bound on the complexity of an algorithm. And I also told you that when we compute the complexity of an algorithm, we need to measure it using some unit, and there are multiple units for measuring or for gauging the complexity of an algorithm, which include the big O notation. Let me go to that slide. Which include the big O notation, omega and theta. But in this particular course, we will always be interested in big O, which shows the worst case time or worst case of an algorithm, because if we improve the worst case, the upper bound or the worst case performance of an algorithm, its average and lower bound automatically gets better in most of the cases, right? It's not guaranteed, but in most of the cases this happens. All right. So now if we see, for example, if we have a complexity function for a given algorithm as 7n minus 3, then its time complexity will be, if you see, we can remove this minus 3, because as I told you earlier that it is insignificant and this 7 will be inaccurate. So what we remain with is this n. So the time complexity of the algorithm, which is represented by this complexity function, will be order of n, right? And then we may have a complexity function like this. How will this be achieved or obtained? Today we will be discussing those examples. Now, if you must have programmed a few examples in your previous course and assignments and the project, which were a bit complex than the basic level examples. And if you can recall any complicated project you may have coded or programmed, you will come to know that there are different segments in your program, right? For example, if in your code this blue line represents one particular task, right? This can be a function, this can be a task, and then these green lines may represent another set of events or tasks which are performed, but they are all in the same file. Okay, and then these yellow lines may represent yet another set of operations which are performed on the data, right? Then and basically what happens is that this code may have, this piece of code may have the time complexity represented here, right? Plus this code may have the time complexity represented here, right? Okay, this piece of code, and then the final segment may be represented by this particular n, right? Because we may have independent units within a same piece of code or within the same algorithm, right? So what we do, we add them, like we compute the time complexity of this blue portion, we write it here, and then we compute the time complexity of this green portion, and then we write it here, plus we compute the time complexity of the yellow portion, and then we write it here. Now if we want to find, or if we want to compute the overall time complexity of this complete code, because this belongs to the same algorithm, So in that particular case, what we will be doing, we will see that among these three, or maybe they can be 4 or 5 or maybe 2, which one is the worst or which one is the maximum, because here we are considering big O order, which indicates the worst case. Now among these three, if we see this n is the smallest number, and n square is a rather bigger value, which is multiplied by 5. But if we see here n square is multiplied by, and again if I can make you recall that this 5 is going to be removed, this 8 is going to be removed, right? So here if we see n is the smallest, we cannot consider it. N square is bigger, but there is another term which is more bigger than this one, which is n square log of n. So the overall time complexity for this piece of code will be order of n square log of n, because here we are considering the worst case. It means that the 3 segments of the code, like this blue one, then this green one, and then this yellow one, where if I recall correctly, earlier I was telling you that for example this blue one is represented by this time complexity. So the overall execution of the program is dominated by this piece of code. The major bottleneck is this piece of code, and now we know that this the overall execution of the program is dominated by this piece of code. Then maybe if you want to improve the quality of the code so that it may execute lesser time, then we may concentrate on this segment of the program only to improve the performance in terms of execution time, right? So now these are the performance classification. The best performance is order of 1, right? Okay, this needs to be explained. For example, we have a piece of code which says for I is equal to 0, I is less than, let's say, n, and I plus plus, right? This is the piece of code, and some processing happens here, right? And we have another piece of code, for example, which says for I is equal to 0, I is less than 500, I plus plus, right? Now when we compute the time complexity of this particular piece of code, we know that this code is going to execute n times. So instead of going into the details, the overall time complexity of this piece of code is order of n, where n may be any number, 10, 100, 500, right? So this is dependent upon the input size n, right? But if we come here, if we see the time complexity of this code, and here this is not n, this is 500, so its complexity will be order of, yes, you're right, order of 500. But remember that this 500 is a constant, right? So order of any constant is always equal to order of 1, right? So it means that this code, this red piece of code, is always going to consume the constant amount of time, irrespective of the size of the input, because here the loop or the piece of code which is in red is not dependent upon any input value. So it will always consume a constant amount of time, whether it be 5,000, whether it be 5 lakh or 5 million. So its time complexity will be order of 1, right? But in the blue piece of code, the execution of the code is dependent upon the input, right? Input may be large, so it will take larger number of iterations, and if input is less, it will consume lesser number of iteration. So here the time complexity is order of n, right? So again, let me give you another example. For example, we have another piece of code. Okay, let me write it, and that piece of code says cout hi, right? Now this piece of code is a single line, and this code also has the time complexity of order of 1 because it's a single piece of code, right? It's one line, right? So remember, anything which is constant, if you are discussing, if you're considering a piece of code with constant number of iteration, its complexity will always be equal to order of 1, and order of 1 is the best. This is the minimum amount of time an algorithm can consume, right? So now let us come back to the performance classification of various types of code. Later I will be giving examples here. Now the order of 1 is the best, right? This is the best. Then something which is like more time consuming as compared to 1 is log of n, right? Then the order of n, which is a linear time consumption, that is a bit high on the higher end. Then n log of n consumes more time. Then we have quadratic n square, which consumes more time. Then we have cubic, or we can have n raised to power 5 or 6. And then the worst one is 2 raised to power n. It consumes a lot of time, and even we can have something like n factorial as well, depending upon what you are coding, what you are programming. So n factorial is the worst one, right? Now if we have to analyze the performance or of any algorithm which takes this much time, we need to see that on the larger inputs, right? For example, now if you see here, what happens if we double the size of input size, right? If you see here, okay, if you see here, n is the size of the input. Initially, let's say we give an input size of 8, and then we double it 16, then we double it 32, and so on and so forth. So for a given algorithm which has a time complexity of log of n, there is another algorithm which has the time complexity of 5n. Another algorithm has time complexity of n log n. Another algorithm has the time complexity of n square. And finally, the last algorithm has the time complexity of 2 raised to power n, right? Now, if the input size is of 8, this n log n is going to consume only 3 steps, 3 unit of times, right? But if the 5n is going to consume 40 units of time. Now, there is a hell of a difference between 3 and 40, like 37 units of time, there is a difference. Then n log of n consume 24 units of time, n square consumes 64, and if you see here, these are 3 digits. This for the same input size, this exponential complexity algorithm 2 raised to power n consumes 256 units of time, right? Now if you see, when we double the size of the input, that is we go from 8 to 16, there is a very less difference observed for a logarithmic algorithm. It jumps from 3 to 4, no difference. But if we see it for the exponential time complexity algorithm, it jumps from 256 to 65,536 by just doubling the size of the input, which is very huge. But if you see, similarly, if you see here, now if you see here, as we double the size of the input, this exponentially executing algorithm jumps makes huge jumps from running time from one to a higher figure. But as compared to this one, if you see this logarithmic, there is very less peak. There are very less peaks as you go from lower size input to the higher size input. It means if we may draw it using the graph. Now this okay, let me represent it using green line, and let me represent this exponential one using blue line. Now this green line is going to, and this is time or size of the input, this is time. Now this green that is the logarithmic algorithm is going to run like this. Okay, as the input size increases, as the size increases, is its requirement and time increases, although but this decrease is very like minimal or slow. Whereas this exponential, as the size of the input increases, it goes from here to here, right? So for minor increase in size, there is a huge increase in number of steps or the execution time, right? So we need to write good code. Now size does matter. Suppose an algorithm has a running time of order of n factorial, right? Now this n factorial is the worst one could write, and we write it for small problems, but for example if the input size is 3 or 5, n factorial may consume unnoticeably large amount of time. But as the input size goes from, let's say, beyond 3 or maybe beyond 10, the execution time is far much more. So, and let's assume that if n is equal to 10, the time actually which is spent is 1 second, right? Now if n is equal to 12, the running time of an algorithm which has a time complexity of order of n factorial is going to be 2 minutes, and 2 minutes for an input size of 12. You give it an algorithm, an array of 12 elements, and it gives you an output in 2 minutes, right? So 2 minutes is a huge time. Okay, let us count it. 1, 2, 3, 4, 5. Rather, we can do it like this. Okay. Oh, and within 5 minutes we started to get bored, and if an algorithm gives you an output after 2 minutes, right? So it means it's a very poor algorithm. Then if we have a slight change in the size of the input, we jump from 12 to 14. It jumps from 2 minutes to 6 hours, right? And then if we jump from 14 to 16, it jumps from 6 hours to 2 months, right? Assuming that 10 steps will take 1 second. And if we jump from 18, it makes a very huge jump. It jumps from 2 months to 50 years only. And remember, this will be an algorithm. This will be a finite set of statements that will guarantee an optimal solution in a finite interval of time. But it will be a very poor algorithm, right? So this algorithm may satisfy the condition of the algorithm, the definition of the algorithm, but if it gives you answer in 50 years, it's of apparently no use. And if we give it an input size of 20, this is going to consume 200 centuries to give you the correct answer, right? Now let us have few examples of analyzing the piece of code to compute their time complexity. Now first of all, in the code we analyze the constant time statements, as for example if you take the example of this code, we initially identified the constant time statements, right? Then okay, let me go to the slide. Yes, then we analyze the loops, then we analyze the nested loops, and then we see the analyze the sequence statement or if else conditions, right? So let's go to a simple example. Now all of these pieces of code, this is a different code, this one is different code, this one is different code, and this one is different code. All of them have a time complexity of order of 1, right, because they are independent of any input value. Now, given this loop, if you see, now this loop, okay, we can say that okay, this is statement number 1, this is statement number, let's say 2, and this is 3 and 4 and 5 and 6 and 7. But as we know that we are going to ultimately go for a bigger picture, if you see here, this loop runs from 0 to n, it means, and there are no other loops, it means that its execution time is order of n. Execution, sorry, time complexity, not execution time, right? So there are 4 statements that run in order of 1. So if we do it like this, ultimately we are going to have the time complexity of order of 1. Now now if you see here, its time complexity, this piece of code has a time complexity of order of 100, and since 100 is a constant, so it will be equal to order of 1, right? So any constant, whether it be 100 or 1000 or 1 million, it will be equal to order of 1, right? Now if you see here, we have 2 loops, 2 nested loops. Without going into the details, if you see here, this outer loop is going to be executed n times, this inner loop is going to be executed n times. For each iteration of outer loop, inner loop is going to be executed n times, so it becomes n into n, which is equal to n square. So we can write it order of n square, right? So this is the nested loop. So this is order of n square. And again, maybe we could have a piece of code like for I is equal to 0, sorry, is equal to 0, I is less than, let's say, n, and I plus plus, okay, and then we within this loop, for maybe we have j is equal to 0, j plus plus, oh sorry, j is less than, let's say, m, I'm using a different variable, and j plus plus, and then we have yet another loop, k, which is equal to 0, k is less than o, okay, and k plus plus. Now we have 3 nested loops, right? So the time complexity of this piece of code will be order of n into m into o, and just in case if this was n and this was n as well, then in that particular case that would have been order of n into n into n, which is equal to order of n cube, right? So this is how this would be for nested loops. Now same goes for this loop as well. These are 2 loops, so this is order of n square. Then if you see here, this piece of code, okay, let me zoom it. If you see this piece of code, these are 2 nested loops, right? This is one segment of the code, this is another segment of the code, and this is the last segment of the code, right? So this segment of the code has 2 loops, so it is going to be order of n square, right? This piece of code has 1 loop, so it is going to be order of n, and this is a constant time statement, so this is going to be order of 1. So this will be order of this should have been yellow, does not matter, okay, but let me overwrite it, right? Now the overall time complexity will be order of n square plus order of n plus order of n. But here this sum works that we have to take the worst of all these three. The worst one is this one, so overall time complexity will be order of n square, right. So this will be the final time complexity of this piece of code, right. So this is how it works. This summing of different segments, time complexity of various segments of the code is called the sum rule, right. Okay, then we may have conditional statements in our piece of code, and what we need to do is we simply, here there is no condition mentioned, but for example this has a time complexity, for example, of order of n, and this may have a time complexity of, let's assume, 2 raised to power n. Now in this particular case, among these two conditions, since we are considering big O, so this is the worst one, so will be overall time complexity of the code will be the one which is the worst, right, among these two conditions, right. So the worst one needs to be picked, and here in the example it's written that statement 1 is of order of n and statement 2 is worth order of n square. The worst one is order of n square, so overall time complexity of the code will be order of n square, right. Then these are a few examples, or before going into these examples, there is one important example which is not in these slides, but I must discuss that, and that is the log of n. When are we going to have the log of n time complexity? Now whenever your loop has a jump of makes a double jump, not a jump of 2, right. For example, if you see here, for I is equal to 0, I is let's say less than n, and I is equal to I plus, let's say, 2. Okay, now this particular example is in any case this is going to be okay, it will take one number, skip other one, take one number, skip, take one, skip. In this way ultimately it is going to be order of n, right. But if you have a jump of a double jump, for example, and how can that happen? Let me show it to you. For I is equal to 0, I is less than, let's say, n, and I is equal to I multiply by 2, right. Here if you see, this is a double jump. So you are skipping from between one number to another, you are skipping a lot of numbers. So whenever your jump is of double, and this could have been so this complete could have been okay, I is equal to I divided by 2 as well. Here you are slashing half of this search space, right. So in this particular case the time complexity is always log, since you are making a jump of 2, so log to the base 2 of n, so, right. So for algorithms where or piece of codes where you make a jump of double, not 2, double, so in that particular case the time complexity is log of n. Now okay, let me Excel, let me show it to you. For example, we have a number 1, 2, okay, for example this is 1, this is this plus 2, right. So if you see here between each number we have skipped a very few numbers, और ये Excel ने काम ठीक नहीं किया by the way. But for example if I have a number 2 and I say okay, this is equal to this multiply by 2, this number multiply by 2, right, and then I say okay, this next number will be this number multiply by 2. Now if you see here, here between 2 and 4, although only one number is skipped, but between 4 and 8 we have skipped 5, 6, 7. 3 numbers have been skipped, right? Now, and as we go from, let's say, 8 and we double it by 2, and if you see here 7, 8, 9, 10, 11, 12, 13, 14, 15, 9 numbers have been skipped. It means that as we are going forward, we are making a huge jump, ignoring or skipping a lot of details, and this makes sure that the execution time is less. So whenever there is a jump of double, in that particular case we will have a time complexity of log of n. Now okay, we will discuss this particular thing in the next lecture, so that we can revise as well and we can have a case study. By the way, this is the last slide of the time complexity, but we will do it in the next lecture. Thank you so much.